Welcome to Engine Builder Live Tech Q&A with Total Seal Piston Rings. My name is Greg Jones. I'm the editor of Engine Builder Magazine, and I'm joined with Keith Jones, who's the Director of Technical Sales at Total Seal. Keith, good morning.
Morning, everybody.
Thanks for joining us, Keith. And thank you to all of you guys out there who have joined us for this Tech Q&A. I'm going to kick it off with the first question. Obviously, Keith, we're all dealing with this coronavirus, COVID-19 pandemic, and it's affected us all in a lot of different ways. So I just wanted to ask you, what's been the effect over there at Total Seal? What have you guys been doing to kind of deal with it? And, has it affected business in any way for you guys?
Question. It says currently, I just had a thing came up. There you go. Thank you. That's kind of a multi-pronged question. Yeah, I think everybody's affected by it in some way, shape, or form. There's no way to escape this, and it's going to be, we'll say it's going to be an interesting ride for a while. That's for certain. As far as Total Seal, no, we're still here. Our state government deemed us as an essential business, so we're still here. But we've got the building closed up. People are not allowed just to walk in and come in and buy parts. They've got to call in, get all the information to us, because we do get a lot of will call customers as far as the physical facility goes. They're not just allowed to walk in and wander around as they have in the past. We're pretty open, and we love to show people the shop. We're pretty proud of our place. So right now that's kind of locked down. That's a little bit different. As far as business goes, no, we're still really busy. Surprisingly, we're querying a lot of shops, talking to a lot of guys, and there are shops that have slowed down. There are areas that have slowed down, but by and large, the word I get is all the time is freaking crazy. They can't believe how much work is coming out from people that are staying at home. They're diving into all kinds of projects that have been on the back burner for gosh knows how long. I know I've personally dove into stuff that I've been looking at for 20 years, and my wife's been reminding me all the time, when are you going to get around to that? Well, I guess it's now. But no, generally speaking, we've been very, very busy. A lot of very unusual calls coming out of the woodworks, all kind of, old engines, odd engines, a little bit of everything. But by and large, we're still very busy. Some of the big customers are obviously shut down right now, so that's a little bit different. But like I said, in general, we're still really busy and doing our best. We're staggering shifts out in the shop to give everybody room to distance. We want to be very careful and very responsible about this. We haven't had anybody here have a problem, nor know of any family members that have had a problem. So by and large, knock on wood, we've been pretty good so far.
That's great to hear. For the attendees, I just want to let you guys know that you can also ask a question of Lake. He is on the call if you have something that you feel Lake would specifically be able to answer. But otherwise, Keith is our main guy to answer questions. So again, feel free to type those into the chat to me or use that raise your hand function to ask questions. But I'll kind of dive right into it here. I got a couple questions from some people before the meeting started. So the first one comes from Steve Glotzbach. And I apologize if I didn't pronounce your last name right, but Steve asks that he says he has used gapless rings in numerous builds, everything from Mustang 4-cylinders to alcohol burning small blocks for front engine dragsters, and had great results and no complaints. However, he recently installed some gapless rings in 2 LT1 engines, one in a 94 Camaro and the other in a 95 Corvette, and both had some smoke, like they had bad valve seals. They smoke when you first fire up and every time you pull away from an idle. But he says both cars have great horsepower and perform well, but the smoke and oil usage is becoming intolerable. He says that they use Felpro valve stem seals on both builds and is just looking for any insight on that situation. And again, that comes from Steve Glotzbach.
Well, thanks, Steve. I really appreciate you asking that question. I'm glad that you've had great success with many of your builds in the past. The earlier LT1, LT4s, as you said, they're kind of suspect to valve guide seal. Even though you can have brand new valve stem seals on it, doesn't necessarily mean they're doing their job. So one of the things to look for, and let me back that up just a little bit. One of the things to remember with the gapless ring is it's really no different than a conventional ring as far as materials, coatings. Second rings are the same, oil rings are the same, and I'm not sure if you're running gapless top or gapless second. But one of the main functions, or one of the attributes of the gapless ring, is it increases intake manifold vacuum on the intake stroke. So when we've got that, overnight sitting situation like you're describing, gravity's feeding oil down, not up, obviously. Extended idle times, we're sitting at a stoplight. We've got, very strong intake manifold vacuum signal at that time. You also see that during, part throttle cruise, where we're making a lot of intake vacuum. Engine braking, engine decel, we're making a lot of vacuum. Well, that vacuum is looking for oil anywhere it can find it from. And there are quite a few sources for that. There is obviously the valve to valve guide interface, valve sim seal interface. We've got cylinder finish, of course. Too rough a bore can lead to an oil situation where we've just got more oil on the bore than what the rings can deal with. You can exacerbate that problem by adding a high volume oil pump. We can get into a whole separate discussion about oil pumps and oil pump volumes. At Total Seal here, we generally don't recommend high volume oil pumps on street cars unless you have a high speed bearing problem, unless you've been experiencing failures. Most of the time, high volume pumps just overfeed a cylinder that's already got adequate oil. Now, there's always exceptions to that rule. There's guys that love high volumes, never have a problem. In my personal experience, oil volume can really be a trick that you got to pay attention to, especially, again, we're talking valve guide seal. We're increasing oil volume, not only to the cylinder walls, we're increasing it to the valve train. You can end up flooding valve train and valve train seals. So those are all things to look at that can be suspect. The first place I'd look, though, is, like you said, when you fire it up in the morning, you get that puff of smoke. It's a little bit of work, and you kind of got to dive into it. If you can get like a bore scope or some way to look down through the intake tract, look for an open valve. Look to see, after sitting overnight, if you see wet oil accumulating on the back of the valve. That's the real true test to look at that valve guide seal interface. Is if, after it sits for a while, are you getting any oil coming down the guide? I've personally worked on those engines where I've taken the old squirt can of oil, what I call the old Duca can, and sat there with the heads on a bench and just sat there squirting oil on the guides and let it sit, and come back an hour later and I've got oil running down the guide. And come to find out the seal wasn't doing its job, or my guide clearance was too loose. I've also seen situations where the guide to the cylinder head had oil coming down at the person that knocked the guides out, kicked a little burr up in there when he knocked the guide out. When he put the new guide in, there was a little, there was a little slot, little groove cut on the inside of the head, and I had oil coming down there. So there are quite a few places that can cause that to happen. But those are places to look, some things to look for. If you want to reach out and contact me directly, we can dive deeper into types of oils, bore finishes. There's lots of things that can affect that. But everything you're describing to me looks like would be an upper end issue, especially since you're seeing that up when you first started. And that would be the first place I'd look.
Excellent. Steve, if you're on the call, does that answer the question for you? Is there anything else you'd like Keith to explain there? All right. We got a question in from Derek Dixon. He asks, what are some key pointers that should be addressed when rebuilding aluminum block turbo engines, like a 3-liter Ford Duratec V6? He says that he experienced some crankshaft flex on the engine, and a custom crankshaft is not an option due to cost.
Well, the biggest thing with the aluminum stuff is just that it is aluminum. Now, I'm assuming it's got an iron cylinder in the engine. We're not talking about alusil or Nicosil coated bores, which are other questions we can answer. But with aluminum stuff, it's the precaution of doing everything you can to simulate a bolt-in situation. Meaning, torque plates. There's customers that I have that go to the extent of, if it's got they'll hang a bell housing on it. They'll hang, they'll mount it the way it's mounted. They will do everything they can to replicate, the fastener loads on the engine to move the deck, move the mains, move the bell housing area to try to replicate everything. I can tell you, like pro stock guys are fanatics about doing this, and that's a thick iron block. So anything you can do in the aluminum block to simulate that, bolted in condition is going to help to move all those things and align them prior to doing your mains, prior to honing the cylinder. Another thing to look at with aluminum blocks, And this really pertains to every block, but it's particularly useful in aluminum. And not a lot of guys talk about this, not a lot of guys go into this, but is what's known as vibratory stress relieving. The old adage of a seasoned block comes back to, the block's been heat cycled so many times that it's finally stopped moving around. And you can do some Googling on this thing. Joe Mondello, God rest his soul, did a huge article on vibratory stress relieving Oldsmobile blocks, and showing he would take blocks that have 100,000+ miles on them, put them on a vibratory stress relief table. One particular brand's a metal axe. Put them on the metal axe, let them vibrate for 24 hours, and then measure how much that block, that 100,000-mile block, moved around in every dimension. Once he vibratory stress relieved it, it stopped moving. I have many, many customers that work with aluminum blocks, sprint cars, drag race stuff, billet drag blocks that have all gone to vibratory stress relieving the aluminum, and how much these things stop moving around. Once they do that, then they'll do all their final machine work and they just stop moving. I have one guy took a brand new set of aluminum heads, put them on the vibratory stress relief table. After about 6 hours, it dropped 2 of the seats out of the head. So where that goes to is that would have eventually happened in the car. Once it heat cycled enough times to move the aluminum that far, it would have actually done that in the vehicle. So that prevented that. So as far as preparing an aluminum block, you want to do everything you can to replicate the installation. And if at all possible, to get it on a vibratory stress relief table, you'll be blown away at how much it moves and how much it settles down and how much it stops moving after that. Hopefully that answered your question.
Yeah, thank you. Thank you, Derek, for asking. Does that clarify it for you? All right. Just in case anyone's gotten on a little late, I just want to reintroduce myself. I'm Greg Jones, the editor of Engine Builder Magazine, and we're here with Keith Jones, who's the Director of Technical Sales with Total Seal, and he's answering all your tech Q&As, tech questions rather. And again, if you're looking to ask a question during this Q&A session, you can either type it into the chat, which is an option at the bottom of your screen to open the chat, or you can go into the participant area button there and raise your hand and ask a question that way. But anyway, moving on, Sadell Martinez asks, what is optimal as far as wanting to achieve or create pressure state between the piston rings? Do you want a pressure difference, or do you want an equal pressure between rings in order to create that desired state?
Well, rings run as, rings are a pressure back design. There's always going to be some pressure behind the rings. So as far as, equalizing pressure across the rings, that kind of leads to the whole ring flutter discussion about trying to get that balance, trying to relieve pressure. But rings run in a pressurized state. Even in fluid engines, steam engine, non-combustion engines, they still run in a pressurized state. They've got to get some type of pressure behind them to gas activate. So that's really where it comes down to. The whole equalization of pressure, more pressure above, more pressure below, the ring flutter theory is a very arguable, debatable theory. It is a theory. It holds water. It works in a computer. It works on paper. In my experience, in all the years that I've been here, it's a very, very specific environment that it takes to actually create a true ring flutter situation. Many, many, many people, the lion's share of people, kind of self-diagnose. It's like going on WebMD. You type in, you got a sniffle, hey, you're dying of cancer. No matter what you do, it's a worst case scenario. Not trying to make light of that. But a lot of people self-diagnose that as being a problem. And most of the time it's just bad ring seal. I've had people tell me they see chatter marks in the bore. Well, that's a lack of lubrication. That's a ring going dry. And they've attributed, oh, I've got ring flutter, I've got chatter marks. So, to answer the question, it is, you're always going to have pressure behind the rings. You're going to have more, of course, behind the top ring than you're going to have behind the second ring, simply because it's exposed to the flame front combustion process. So there is a reduction in pressure as the rings descend down the piston, but there's always going to be a pressure there. Going to the ring flutter portion of it, like I say, it takes a very specific environment to create that situation, which most engines simply aren't efficient enough to do. Again, if they want to reach out to me, talk to me more about a specific application. But to get into that environment, it takes an extremely efficient exhaust side of the engine to truly create that, where we're actually evacuating the cylinder faster than the piston can push it out, which is on paper, again, what we all desire in the engine, but is in reality, very, very rare circumstance, very rare occurrence. I'll cite an example. A lot of guys say, oh, you can't run a gapless second ring. It doesn't let the pressure out beyond, past the top ring. It gets in, it traps, it's going to create ring flutter. Well, I can say emphatically that, thousands and thousands, tens of thousands of engines have been built and run with a gapless second ring that have absolutely zero ring flutter issues. Diesels in particular, we service tons of rings. I'll point out a specific customer, Shaver Specialty, Shaver Racing Engines. Ron and the great guys at Shaver run gapless second rings, and they're absolutely outstanding sprint car program. Have been running gapless second rings for longer than I've worked here, which is going on 24 plus years. These engines run in excess of 9,000 RPM, make close to 1,000 horsepower these days. They don't have a ring flutter problem. So again, go back to my dad's 76 Chevy Vega, where the second ring's tighter than the top rings in that engine. Absolutely, we've been building engines with the second ring tighter than the top for over 100 years. Did that engine experience ring flutter? Absolutely not. So it takes a very specific environment to create that scenario. But to answer that question, like I said, there's always going to be pressure behind the rings. If they don't have it, that's going to be a problem. It kind of leads to like gas porting and things like that, which we can expand on as we go. And hopefully I was able to answer your question.
Yeah. Thank you, Sadell. We appreciate the question. You mentioned shavers, Keith, and Don did ask a question. So I'll go ahead with his. He says that he's got a question about Total Seal's new gas-ported rings. For years now, they've been working with gas-ported pistons at shavers, mostly from Mala Motorsports, for 410 Outlaw engines. And because of that application, they've had to use horizontal ports instead of vertical. He says that he and Lake are going to be testing those new gas-ported pistons soon. But he says he has a few more cylinder wall flex issues from the all-aluminum Donovan block that makes his job a little bit harder. And he thinks the added grooves in your ring will help the ring conform to the distortions in the cylinder wall better. So his question is, should he change the radial depth of the groove for the new ring? And what are your thoughts on keeping the same end gap with the new top ring?
Okay. A lot of things to cover on that one, and I'll try to make it quick. As far as to answer Don's questions, quickly and easily, no, end gap's not going to change. Back clearance between the ring and the ring groove is not going to change. We want to keep that back clearance between the land and the ring as tight as possible. Most people shoot for between 5 and 10 thousandths. We've got to give the piston adequate room to expand and not push the ring out of the groove. As the piston expands, it expands from the middle out. And if you're not running enough back clearance, you can actually have the piston, as it grows, the ID of the piston can actually push the ring out of the groove. Now, some people look at a piston. Let me grab one here. Here's an old super stock piston from the 70s. This piston's kind of built like a can of beer, kind of straight up and down, runs a lot of loose piston to wall clearance. This one's a more modern piston. This one's shaped more like a keg of beer than a can of beer. Small at the top, small at the bottom, big in the center. That's our gauge point. So some guys will measure the piston across the top and see it's about 40 thousandths smaller than the bore. And they'll kind of calculate back clearance on the ring. Well, hey, it's 40 thousandths smaller. Well, that's sitting here at room temperature. When it's actually running, the piston at the top is actually slightly bigger than it is at the bottom. So you've got to be real careful about how much back clearance there is to have the ring not bottom out in the groove. So anytime you fit the rings to the piston, you always want to take the ring, put it in the groove, make sure it goes down into the groove, not compressing it, just letting it fall down into the groove, and it should always lay slightly below the edge of the land. That way you're sure it can't bottom out. So to answer his question, now end gaps are going to stay the same. As far as back clearance, 5 to 10 thousandths is typically where we want to be. That's kind of the number we're shooting for. Those are where you want to be. Now I'm going to touch on the gas port bit a little bit. So I'm going to try to keep this as quick as I can. This is our gas ported piston ring for those who haven't seen it. As you hopefully can see, what we've done is put the radial slots in the ring, kind of mimicking, again, kind of dark and hard to see, the radial ports or lateral ports that are in this piston. What we have found with putting the gas port in the ring versus the piston is When they're in the piston's not rotating. Rings rotate in an engine. They're always turning. So what we find is, especially in like aluminum engines, alcohol engines, that we'll see concentrated wear lines in the bore, right where every gas port lines up in the piston. It's a high pressure point. So having the piston gas ported in this case is good. We're getting more pressure behind the ring, helping to get that pressure out and blow the ring out. Again, the ring gas activates. But one of the advantages to putting it in the ring itself is the ring's rotating. So we're not getting that high pressure buildup. We're not getting that high pressure point. So we're distributing the pressure more evenly around the bore. We see less bore wear. We see improved ring seal. I've had many, many customers literally back-to-back AB gas ported piston, conventional ring, non-gas ported piston with a gas ported ring. I've yet to have a customer that didn't pick up power and lower blow-by. That's not knocking the gas port in any way. We just truly feel that this is more effective. And one of the things that makes this more effective and why is that gas port location is very, very critical, how deep it goes into the piston. And I've got a sample here I'll show you. As he mentioned, the mala piston, here's the top portion of a mala piston. Customer sent this thing into me. We dissected it so we could do some hardness testing, look at groove wear, and we actually, on the wire EDM, cut it right through the ringland. So we get some hardness tests and roughness tests. If you look at that gas port, you'll notice that port goes just to the back of the groove. It doesn't actually go down into the root of the groove or the inside diameter of the land. What happens if it gets down into the root of the groove, and I'll kind of draw this on the board behind me, hopefully you guys can see me.
Yep.
I'm looking here, make sure I'm not off the screen. This is the ring groove. Really bad version of it. I've got the ring in the groove. And what happens if I get the gas port too far into this back area behind the groove, I actually create a lake path, not a lake path, a leak path around the ring, and I can create reversion on the intake stroke. So if I get that gas port too far back, the ring can't seal the gas port off on the intake stroke. And that's readily seen when you look at the piston. If you look at the gas ports, you see all this black, gooey, gummy nastiness coming up back up out of the gas port. That's reversion on the intake stroke. And what that's telling you is they've got the gas port too far behind the ring, and it's not able to seal the ring off on the intake stroke. So ideally, you want the gas port just to the back, whether that be a vertical or a lateral. We don't want it to go too far behind, or at all if possible, behind the ring, because you're creating a pathway. Especially on a vertical, I've seen vertical ports that were milled all the way down to the bottom of the land, and they've had nothing but ring seal problems, and it creates reversion all the way around the ring. You see all this black, nasty, gummy stuff coming back out. At the same point in time, I've had people that have had problems with ring seal, and it was simply because the gas port ended up here. It wasn't in the right spot. It was a lateral that came back and didn't get to the back of the groove, or a vertical that came and it was too far off the back of the land. So effectively, it's not really doing much of anything. It's getting gas pressure in, but it's really just kind of pushing down on the ring, not getting behind it and pushing out on the ring. So gas ports are a great thing, but we always have to check them. You can do that easily with just a set of pin gauges. Drop it into the gas port, either whether it's a vertical or lateral, make sure it's right at the back of the groove. If for some reason it's way behind the ring, that can create a problem, or too far off from the back of the land, that can create a problem. It should sit right at that back corner. By putting it in the ring, it's never in the wrong spot. It's always in the right location, because I'm not dependent on the gas port being in that exact right spot. And again, I'm not picking on any piston companies in any way, but if you get that situation, you've got one, you just can't seem to figure out why it won't seal up, everything looks right, the cylinders look good, the rings fit nice, check that gas port location. That can be an issue, and has been an issue in some applications in the past. So one of those things that we need to look at, just like everything else. We need to, we got to look at bearings. We got to check everything. Check your gas port location. If for some reason it looks like it's way off, you want to get a hold of the piston guys before that and say, hey, what do you think here? So that's kind of a lengthy explanation, but I wanted to give you guys that information.
Yeah, Keith, kind of touching on what you were talking about with the ringland, we have Del Segura asked, how snug should a ring fit into the ringland? Is a tight fit, you know, more desirable than a loose fit? And does material make a difference?
Okay, that kind of comes down depending on how much vertical clearance. Again, I'm going to go back to the board here. When we start looking at the ring groove interference of the fit, again, we're all talking about getting gas pressure behind the ring. We have to get gas in the ring. So as far as the clearance, yeah, we want it as tight as we can get it without micro welding or getting a situation where we start to actually melt the aluminum onto the ring. Sometimes if you've got an engine that lost the tune-up, turbo car, nitrous car, something that ran very lean, you can actually weld the ring, called micro welding, actually melting the aluminum of the groove onto the ring, and then the ring sticks. Once the ring sticks and stops turning, it can't lubricate itself, and we're just literally putting gasoline on the fire at that point. It's just going to go from bad to worse really quick, and it can lead to absolute engine devastation. You want to run the rings as tight as you can without getting into micro welding. But through a lot of testing, through a lot of customers, a lot of modeling, we also see that right at about 1.5 thousandths clearance between the ring and the groove, we start to see the amount of pressure that can get behind the ring start to diminish. So as this number starts to go down, this amount of pressure is going down with it. And right about at 1 thousandths, we start to get to a point where we're not getting enough pressure behind the ring, and we're starting to actually lose ring seal. So that clearance comes down to, back to what we just talked about, gas ported or not gas ported. Once we hit about 1 thousandths, you really are going to need to have a gas ported piston regardless of what the type of application is. Simply, you get enough gas pressure behind the ring to keep that ring gas loaded. If you're running a non-gas ported piston, generally between about 1 thou 2 to 1 thou 5 is kind of the sweet spot. You get enough gas pressure behind it, keeps the ring loaded, not an excessive amount of clearance to where we're starting to get into ring chatter, excessive ring groove wear. But if we do have a gas ported ring, now we can start getting below 1 thousandths, typically around 0.8 to 1 thousandths. Again, this is kind of a long explanation, but it's a good question. The other thing that comes into play is how good is that ring? You got to remember that a production piston ring, if you go buy just an everyday iron ring off the shelf from many, many suppliers, this dimension, what we call the axial height, the dimension from the top to the bottom, is typically 5/10 thousandths. So if you buy an off-the-shelf piston ring from most companies, let's just say, for instance, it's an 043 ring. Well, the nominal size for a 43 ring is 42.5, plus or minus 5/10. So that means that ring can be as thick as 43 or as small as 42, and that's in production spec. That's a production spec ring. So if you're trying to run a ring groove that's only got, say, 6/10 clearance in it, how can you put a ring in it that's got plus minus 5? You could literally lock the rings up. So now you've got to get into a better quality ring. You're moving into like our AP rings, our diamond finish rings, our gold finish rings. You're getting into a ring that's beyond production level tolerances. Those rings can range from plus minus 1/10.5 all the way down to tight as 50 millionths of an inch. So again, kind of a long answer, but generally speaking, in a non-gas ported piston, about 1 thou 2 to 1 thou 5. Once you get into a gas ported piston, 1 thou or slightly under 1 thou, and then you get into the really high-end stuff. You're the NASCAR, pro stock engines like that. Those guys running them as small as 3/10 and 4/10 clearance. So it was a long answer, but hopefully that answers your question with a little bit of knowledge behind it.
Yeah, excellent. Del, like Keith said, hopefully that sums some stuff up for you there. Bill Hancock asks if you could review some of the keys to evaluating rings on the dyno. Are there some keys to making sure that ring seal is appropriate when you're running the engine on a dyno?
Well, sure. Again, that's a multi-point question. Things to look at when you're going in on the dyno. I mean, before you assemble the engine, a couple little tips and tricks, I'll say. Knock this off here real quick. Things that you can do prior to running the engine at all, just simply during assembly, is when you're putting the engine together, if you want to go through it, we do this beforehand, but you can always do this. You can do what's called a light tight test on the ring. So once you've got the cylinders honed, you're happy, everything's ready to go for final assembly. You can simply take the ring, put it in the cylinder, square it up, and once you're sure it's all squared up, take a little single LED flashlight, take it up underneath the ring, look at the ring around the cylinder. Make sure you don't have any excessive light coming between the ring and the bore. It's what we call a light tight test. We do that here. We've got dozens of light tight stations in the shop. We're constantly looking at light tight here during the production of the part. So you're looking for light tight around the ring. So that's a thing to look for. If you see little like pin dots, little speckles of light, we call it bury light, that's pretty normal. But if you're looking at the ring and you see, you know, an area an inch long, ½ inch long, different places around the ring, that ring's not touching the bore, that ring's not light tight, and that's throwing up a bell. So now it comes down to, is it the ring or is it the cylinder that's not straight around? So something's off. Switch some different rings and see if you see it. You know, to have a ring out of light tight is one thing, but to have 8 rings out of light tight, that would be very, very unusual. So if you drop 8 rings into that bore and they all look not light tight in the same place, you've got a cylinder problem. So those are some preparatory things to look at, just double checking the rings, make sure everything's light tight going in. Another thing to look at is to look at what's called the free gap of the ring. When we build the engine, you know, we're writing down all the data, bearing clearances, you know, spring pressures, you know, we're writing all this down. This is what we call the free gap. If I take that ring and just lay it on the table, take a pair of calipers, measure that gap, that's a free gap. You want to record that. That's an important number. And that's a great post-run inspection part to look at. So engine goes in, it runs, we do our thing. It's normal for this gap, let's just say for argument's sake, that's 500 thousandths. It's very normal for that gap to close up around 80 to 100 thousandths once the engine's heat cycled a few times. It's not normal to have that ring come out at 100 thousandths or 200 thousandths. And it's not normal to have it come out with the gaps, the ends staggered. That's a ring that's gotten overheated. It's losing its tension. It's actually, some people call it annealing. It's actually called creep. You're creeping the metal. But the bottom line, what that tells us is we've got a ring that's either not right for your application or something happened and you got it overheated. So those are some things to look at pre and post running in. Now running it in, my break-in process is to use a good quality break-in oil. We've had extremely good luck with the driven stuff. Hey, Lake, how's it going? And that's got nothing to do with that. It's been a great product. Thanks to Lake for driving that ship for so long. And let me just comment, we're so proud and so glad to have him as part of the Total Seal team. I just can't tell you how great it has been working with him, even in this short period of time that I've been with him, but I've known him for years, a lot of years. It's great, and we're really glad to have him on board. But with that little plug, use a quality break-in oil. My general process is to get it on the dyno, get a mild load on it. If it's a vacuum engine, do not run it in on vacuum. Let it free breathe at all possible for those first 10, 15 minutes. Let the oil get on the parts that need to get on the oil. Instead of letting 20 inches of vacuum suck everything dry and prematurely wear everything out. So warming the engine up, let it free breathe, let it start coming up to temperature. Once you've got some heat in the thing, now put some mild load on it. 50, 75, 100 foot-pounds, all depends on the power level the engine's gonna make. Kind of hard to put 200 foot-pounds against a Pinto. Might be a little bit tough. Probably end up looking at the bottom end, laying on the floor pretty quick. So put a respectable amount of load on it. Let it run about 15 minutes. Kind of like you're breaking an old flat tap of cam, and move the RPM around, up, down. Don't let it sit at any one spot for too long. After about 15 minutes of that, my own personal thing is I shut it off, I come back out, I run the valves, I check the timing, I check a couple spring pressures, make sure nothing stupid's happening. Trust me, you can't believe how many I found that we're getting ready to ventilate and make a real mess that we caught at that point in time. Then fire it back up, and as I like to say, let the beatings commence. Now just start putting power runs on it, looking at everything. And the bottom line is, if you're looking at vacuum numbers, the vacuum numbers should stabilize very quickly within the first 1, 2, 3 pulls. They should flatten out. Power level numbers should flatten out very quickly. Exhaust ports should be nice and dry very quickly within just a few pulls. If you get into an engine that needs, you know, I've had guys on the phone, oh man, we got 12 hits on it, I got 15 hits on it. It's really starting to come in, man. She's really starting to dry up and make some power. That right there tells you got a cylinder finish problem. Because when it comes to seating up piston rings, it's about 80-20. As I mentioned before, we light tight check the rings. We OD lap the surface of the rings. We've done the bulk of the work for you. Now the cylinder finish is the other part of it. And remember that, you know, that running in process is the final machining step. That is the final work that's happening during that run-in process. The rings always plateau the cylinder finish. They're always working on that bore finish. You go back to the 1970s when we're working on 5/64 rings that have 7 pounds of tension and 3/16 oil rings with 20 pounds of tension. You could get away with a lot. And a cylinder that was 150 Brunel, my sister could hone that and get it right because the rings were going to fix that cylinder, very, very quickly. In today's world, where we're dealing with extremely light ring tensions, much, much harder blocks than we had before, we've got to get that bore finish right. And if we get it right, everything on that dyno will come in right now. It'll be in 2-3 hits, that's it. If you're taking a long time to get it in, either we've got something in the oil not happy, we've got something that's too slippery, not letting the parts wear together, or we've got a bore finish that's kind of really out in left field. So again, kind of a lengthy answer, but I wanted to give you all the details to everybody. Those are all a little food for thought.
Yeah, no, that was excellent. Bill, thank you for the question. I'm going to move to Anthony Maines. And again, I apologize if I mispronounced the last name, but he also had a question about running the engine on dyno and using gapless top rings. He's noticed significant improvements in vacuum and blow-by numbers, but they don't seem to translate to higher horsepower numbers. And he's curious if that's normal on the dyno.
No, generally not. I almost always see a power increase, but the dyno is it's not only a tool to look at power and torque numbers, it's also a tuning tool. So one of the things, and some guys don't always catch this, and I apologize if you did or didn't, things that you have to look at power-wise. One, if we're comparing apples to apples, we have to first and foremost make sure we're comparing the same oil ring tensions. So if we go from one set of rings that has a 22-pound oil ring to a set of rings that has a 10-pound oil ring, well, there's going to be a power difference in the oil ring. And I've had guys that have run engines, with a gapless set with a standard oil, but the previous set was a conventional with a low tension oil. So that can be a little deceptive right there. So we have to make sure we're comparing apples to apples. The other part is we've got to look at how the gapless ring affects the intake stroke. The gapless ring, especially in a carbureted engine, almost always pulls more fuel through the engine. So we've got to look at brake specifics. We've got to look at air fuel ratios. Where I've had people in the past that, they put the gapless ring in and they just didn't see the gain. The engine's almost always gone rich. And it's either leveled out. And I've had engines that have lost power because the engine simply went very, very rich. They weren't looking at those numbers. One particular guy, I won't get into his name, stocker, super stocker builder, built an engine for a very well-known man, put gapless top rings in it. We lowered the oil ring tension. He could feel how much easier the engine turned over, yet it was down on power. Well, he didn't have all the dyno figures from the previous build. Once we started overlaying the numbers, the brake specifics went through the roof. The air fuel ratios went down the toilet. Once he got that brought back in line, got the air fuel ratios where they needed, the thing ended up picking up 16 horsepower. So generally speaking, if I don't see a power increase, it's normally something to do with the tuning and generally carbureted, especially with water jets. They're real sensitive because all the gapless ring's doing is making it a more effective pump. As he stated, more vacuum, less leak down, we're building more cylinder pressure. If we're not gaining power, it's generally something to do with the tuning curve.
Very good. All right. Brendan Baker asks, your opinion on what works better, a lateral gas port or a vertical gas port, and how do the top rings differ for those applications?
Well, as far as the top ring goes, it really doesn't differ. It's the same. Like we kind of talked about before, I can't say personally that I've seen a engine dynoed back to back that really saw a difference with correctly done gas ports. Both, as I showed earlier, in the right locations, I really didn't see a big difference there. One of the things to keep in mind though is rings that have that inside bevel. Okay, that chamfer is there to put what we call twist in the ring. It actually makes the ring, if you take a ring with a bevel, squeeze it tight, you'll actually see the ring twist upwards like a Belleville washer. That's the point of the bevel. That's what it does. But when you get into a vertical gas port, a lot of rings today don't have that bevel. Rings are, there's a lot of companies getting away from putting twist in the rings. Most of our rings do have them. Some do, some don't, but the bulk do. But there are companies that are getting away from that. So you lose that bevel. Again, with that vertical gas port, I have seen situations, and let me grab my sample here. Vertical gas ported piston, if you can see that. Where the customer had a vertically gas ported piston, they had a ring that didn't have that bevel. It didn't have that chamfer. And when the ring was installed on the piston, closed down, if you actually looked through the gas port, the only thing you could see was the ring. There was no chamfer, there was no anything. We got back to that situation where the pressure was pushing down on the ring, it wasn't pushing out on the ring. So that's about the only time that I've seen, you know, a lateral versus a vertical become an issue, was simply with that combination, you know, that mix of parts where he had a non-beveled ring in the, you know, the gas port was a little bit off the back of the groove and it was pushing down, not out. It's about the only time I've actually seen it create any kind of a difference. Only other, we'll say, negative, and today it's really not a big deal because you don't see it that bad. Vertical gas ports are more likely to plug up faster than a lateral gas port. So as you can see, the diameter of the hole is much smaller. That's about a 39 thousandths diameter orifice. Trying to find one here to make it easier to see. Wow, shot that across the room. That one, that's about a 50 thousandths, but it's only about half of that. So it's a little larger, less likely to plug up. Vertical gas ports can plug up if you're doing them in street cars or engines that don't come apart regularly, get cleaned. This particular piston that came into me about 2 weeks ago, this gentleman was having some issues. Piston's been run 3-4 times, and every one of these gas ports, though he didn't realize it, was plugged up. I took a 38 thousandths pin gauge, cleaned out every one. He now is going to buy new pistons, but he had no idea that all the gas ports were plugged up on this piston. So that you do have to watch that on them. If you pull the engine apart, take a little gauge pin, clean all the gas ports out. But that can happen with a vertical.
Excellent. Brendan, hopefully that answered that question for you. Keith, we have a Joe McCoy who asks about running oil restrictors in the pressure channels in the block and keeping high volume to the back of the pistons via rod to crank clearance, especially with nitrous for piston cooling. Is there anything he has to know there?
Well, I think he's alluding to to adding piston sprayers. Maybe that's his question. The things that you have to watch when you start putting restrictors in the engine, loosening up bearing clearances, loosening up side clearances, the crank to bearing clearance and the rod to crank side clearance are kind of what I'll call volume regulators. As we open up the shell clearance in the housing, more oil is allowed to escape out of there. The next regulator we hit, sorry, I don't have a rod in here with me, is that crank to rod side clearance. That's your next restrictor. So as we open those clearances up, again, yes, we are effectively putting more oil up into the bore. And depending on how far you go with it, yeah, you can actually overwhelm the oil rings. You can just simply start getting too much oil in there. I only have so many pistons in here with me, and that can especially be an issue if you get into pistons. Geez, neither one of these are really good examples, but where we've got a support rail in the piston, where we've actually cut the piston, we've got the wrist pin up into the oil ring groove. And as you can see here, this piston doesn't have that. So the bottom side of the oil ring, which happens to line up right with that area where the rod's going to throw oil up into the cylinder, is not open. It's not exposed. We're going to get the oil to drain back through the drain holes. We open that area up and throw a rail support in there. We expose the area that's behind the oil ring. And that can now become an oil feed, not an oil drain. We're throwing so much oil in here, we're actually feeding oil into the backside of the oil ring and not effectively letting that drain down. So yeah, you can, depending on that specific combination, piston with an oil support rail that's got that back area behind the oil ring exposed, excessive rod side clearance, excessive bearing clearance, and then we throw in a lot of pump volume on top of that. Yeah, you can effectively overwhelm the oil ring and it simply can't drain the oil back down. I can tell you guys a million stories, but I've had a few customers that bought 512 big block Ford stroker kits. And the kit, I'm not saying who put it together, but it had one brand of crank and one brand of rod. These gentlemen approached us. Hey, I've had multiple sets of rings through this engine. I can't dry it up. I need more oil ring tension. And I'm like, stop. You don't put all these different brands of rings into the engine and still have this problem. There's something else going on. Well, the first gentleman was willing to work with me and really start looking at everything. And what we found was just what we talked about. There was a mismatch between crank and rod, between the radius on the side of the crank and the radius in the rod, and he had a really excessive amount of clearance and a big radius. Once he put the rod in that matched the brand of crank that he had, his ring problem went away, dry as a bone. I recently had a gentleman back east build a 4-cylinder engine. I worked with him for years to really optimize his ring pack. They've got a really tight set of rules. And in his particular engine, he decided to change brands of connecting rods. And same thing. He's had this combinations were great for years at Stride. We've really got his oil ring about as light as we can get it. And we went from an 8-pound oil ring, we doubled it up to a 16-pound oil ring, still wouldn't dry the engine up. Said to him, hey, you really need to look at that rod, look at the rod to crank clearance, and look at the radius of the rod and the crank, and do they match? And lo and behold, he put the old rods back in, bang, dry as a bone, back down to the 8-pound oil ring. So it's a great question. It is something, again, it's all those little details that you've got to look at. So restricting that and opening up those clearances can lead to an oil control problem if it gets out of control. Hopefully that helps answer that for you.
Absolutely. And thank you, Joe, for asking that question. Let us know if you need anything else explained there. I'm going to move on to a question from Jill Lunn. She's asking about your recommendation for rings in a turbocharged or supercharged street car with 15 pounds of boost. She's asking if a gapless ring is the best way to go there.
Yeah, in my opinion, yeah, it is. Especially you've got when you've got a single dedicated application, you've got that. Well, I'll coin a NASCAR engine to be, specific. Let me pull that down just a little bit. You've got a dedicated environment where we know this is how the engine's going to run. It's going to have this much oil temperature. It's going to have this much water temperature. We're going to run it this long. This kind of part piston I showed. This is V8 supercar from Australia. We know how it's going to run. We know the environment. You can get things pretty specific, and what I mean by that is oil ring tensions, gaps, top ring gap, second ring gap, because we've run that engine so much we know this is the environment. Now we enter a boosted street car, what I refer to as the dual purpose application. I want to be able to take it out, drive it, run it, sit at an idle, park throttle cruise down the road. I want to do all the things my everyday driver should do, but yet when I decide to mash that pedal, I want it to be hell on wheels. I want all the power and I want it to be right. So we have to build that engine for that worst case scenario. We've got to build it for the 15 pounds of boost. We've got to set piston to wall clearances for that. We've got to set end gaps on the rings for that worst case environment, even though that environment may only be, 0.5% of the time that the engine's actually run, but we have to build it for that worst case scenario. And one of those is the end gap on the piston ring. We have to gap that ring bigger for that worst case environment. If I don't make that gap bigger, you run the likelihood of butting that ring. And like the saying goes, you put the ring in a little big, nobody knows it. You put it in a little tight, everybody knows it. So it's always better to err on the loose side. So with the gapless piston ring, now you've got that perfect dual purpose application. You can go ahead, gap it big, gap it a little extra big just in case. Let's say you end up having to put 87 octane in it instead of your 91 or your E85. Engines run a little on the hotter side. Gap it a little big, be safe, and not have the blow-by that goes with that big end gap. That gap is required to be big because we're generating more heat. But when you're just park throttle cruising, idling, driving, you're not making that kind of in-cylinder heat that we do under hard load. So the parts have to have room to expand. They got to have room to grow. Giving it that extra gap, the gapless allows you to, again, have that dual purpose. I can gap everything big for the worst case scenario, but the 99.5% of the time that I'm just driving the car, you don't have all the blow-by issues that go with that. So hopefully that answers your question, Joe.
Yeah, Jill just said thank you. Since we're on a question, Jill also asked if an anodized ringland changes your ringland to ring gap measurement.
It doesn't change the end gap at all. Again, we're back to that vertical clearance. If it's a non-gas ported piston, I generally like to see about 1,005. Anodizing the ringland, as we were talking about earlier about micro welding, does help to prevent and eliminate micro welding, which in the big picture of things is really a pretty, I don't want to call it a non-event because it does happen, but in today's world, it's not like it was 10 years ago, especially like in NASCAR engines like that, where we went from leaded fuels to unleaded fuels. That was a big deal. Same thing with NHRA classes like that, where we made a big fuel change. Micro welding reared its head pretty bad, but in the bulk of stuff that's out there today, micro welding is really kind of a non-event. I don't see it that often anymore. And generally, if I do, it's a tuning problem, and the customer almost always realizes, oh yeah, we didn't bring on the extra fuel, we missed the timing, the controller died, I didn't pull any timing out of it. It's almost always, you can almost always nail it to some kind of a malfunction of something else.
Very good. Again, thanks Joe for the questions. Let's see here. Mark Bittner, Mark asks,
Hey, Mark.
gas-ported top ring, is it available in a gapless top, or does it use a gapless second?
No, you can combine the gas-ported top ring into just about every and any combination of stuff we do. I'm sure there are some limitations somewhere, but I haven't seen one yet. We've done them as thin as 0.6 millimeter, and they've been effective. So I have done many gapless tops with the gas ports, and they've been really, really good. Mark does a lot of sprint car stuff, but I've seen him in everything from supercharged drag race cars to to sprint cars, dirt track, late models. It's been very effective in everything we've done, and it absolutely loves being combined with the gapless top ring.
Very good. Thank you, Mark. Hopefully that was helpful. Keith, we have another Jill, Jill Gertenetsky, asking what the difference is in heat transfer between a water-cooled engine and an air-cooled engine between the rings and the cylinder wall. Is there a significant difference between the top and bottom ring?
Well, the top ring is the one that's going to do the lion's share of the thermal transfer, but all the rings do, as does the piston itself. As far as the amount of thermal transfer, between the two engines, I'll be honest with you, I've never done a specific study of air versus water. Water is certainly, in my eyes, going to move a lot more heat. You've got somewhere to take that heat to, from obviously combustion chamber to piston into ring to the wall, wall to the water, water to the radiator. You've got an escape path for that to get out, where air-cooled is obviously restricted or controlled by how much air can get across the engine. So the transfer is going to be better with the water-cooled engine, and that's obvious to all of us. The biggest thing that I run into between air and water is end gaps, depending on what kind of air-cooled engine is. I'll give you an example. Let's say 100 millimeter bore water-cooled Porsche versus 100 millimeter bore air-cooled Porsche. The air-cooled engine may only run 7 or 8 thousandths end gap at room temperature, where the water-cooled engine may run 17 or 18 thousandths end gap. And that's due to bore expansion. That aluminum air-cooled cylinder is going to expand so much more than the water-cooled. So we have to run a lot tighter end gap on the air-cooled piece, so that when it comes up to temperature, we've got a desirable amount of end gap to not have too much flow by. So you'll actually end up tighter, end up at that desired place, because we know the cylinder is going to grow. For water-cooled, we don't see those kinds of expansion rates. Hopefully that answers.
Very good. Let's see, we got a question here about the diamond lapped rings. He's asking about what the true advantages are of the diamond lapped rings. Is it because they're more round? Is it friction reduction or oil retention?
The true advantage to the diamond finish ring, and I've got one right here, is what we talked about earlier, is this axial dimension, this height dimension from the top to the bottom side, is how much tighter we're holding those dimensions. Again, a typical production piston ring, the plus minus tolerance on this dimension is about 5/10 thousandths of an inch. The plus minus dimension on this ring is 50 millionths of an inch. So now we're able to take the ring, put it into a groove, and let's say we've got it spec'd very, very tight, 4/10 thousandths clearance between the ring and the land. So the ring is extremely stable in the land. You can't do that with a production piston ring, simply because the plus minus tolerance is too excessive to allow you to run it that tight. So that's the main advantage to the diamond finish ring. The diamond finish ring is typically, and it can be done with any ring to bring it to that tolerance, but typically very, very thin. This is usually the high-end stuff, whether it be F1, NASCAR, Pro Stock, Comp. These are typically rings that are very thin, 0.8 millimeter and smaller. We go all the way down to 0.5 millimeter. This dimension, the radial depth, we're doing rings as thin as 80 thousandths today. That really increases bore conformability, as does, here's one for you guys, you haven't seen it, that's our total conform ring. That's the ring with the radial notches in it. And that really allows the ring to follow bore distortion. You talk about aluminum engines and how things move, especially the modern engine today. We're dealing with aluminum blocks. A lot of these engines don't have liners anymore. They're just coated blocks. They move around a lot. This thing follows bore distortion like you can't believe. And that's our total conform ring. But that's the main thing with the diamond finish, is that top to bottom tolerance is so tight. It's a lapped ring, very, very high inspection level part, and allows us to run those really tight ring to ring group clearances, which really improve ring seal.
Very good. Alex Pavin just joined the conversation, and he's asking, wants to know a little bit about piston to cylinder clearance with the 2618 alloy, which uses more clearance. Can the bigger clearance kill the rings? You know, any advice on that?
Not really. I mean, when it comes to, piston to wall clearance, that's going to come down to a couple of different things. That's going to be the recommendation of your piston company, because they're going to have modeled this stuff. They're going to have looked at it. So, first place to go is to start with their recommendations. If you're within those recommendations, it's generally not any kind of a problem with the ring. The other thing is your personal experience. If you've got an engine that, at a given clearance, every time you pull it apart, you see a little scuffing in the skirt. Well, that's telling you your application is a little beyond what their, normal window is. So let's say you're using a piston, they're telling you to put it in at 4.5 or 5 thousandths clearance, but every time you turn it down, you've got a little bit of scuffing. Well, you may be leaning on your engine a little harder than what they think it should be, or you're just running it hotter. Put more walled clearance in it. If you're seeing scuffing in the skirt, you're seeing some scuffing in the ring lands, the first thing to do is use your personal experience as the builder and increase that clearance. Talk to the piston guy, say, hey, this is what I'm seeing, and I think you're always going to get that recommendation that, hey, maybe your application needs a little more clearance. Where that number kind of comes into play with us is it's more about what we call rockover than piston to wall clearance. If you had, like I was showing you earlier, this piston likes to run a lot of clearance, 10 thousandths, 15 thousandths, because it's a very straight up and down piston, like I said, more like a can of beer. When it hits top and bottom dead center, it doesn't have a lot of rock. It doesn't move much. It's very stable in the bore. Rings like a very stable piston. They don't like a lot of motion. The more the piston rocks every time it hits top and bottom dead center, it's trying to pick the rings up off the cylinder wall. And we can get into a scooping or cupping effect where they actually start to scoop oil up the bore. You're literally picking the rings up off the wall. So it's really more about rockover than it is piston to wall clearance, because with this piston at 15 thousandths piston to wall, if I use the right ring and I set the end gaps, the ring's doing its job effectively. But if it's got a real aggressive shape, cam and barrel, where you may only have 5 thousandths piston to wall, but it's got a tremendous amount of rockover. One of the things you want to look at, especially with stroker engines, especially with the pistons coming out of the bottom of the bore, you've got a 1/2 inch, 3/4 of an inch, whatever it is, hanging out of the bottom of the cylinder. When you put this thing together, you want to mock up one hole, piston, rod, crank, put it in the cylinder, put it in up, bring her down to bottom dead center. Take the piston, rotate it on the wrist pin until one side hits the wall. Take a dial indicator, which, sorry, I don't have one here, dial indicator on the pan rail, tip of the dial indicator on the skirt of the piston, and then rock it back. See how much rock you've got at bottom dead center. What we've seen over the years is when we start seeing numbers in excess of about 30 thousandths, and keep in mind, it's not a finite number because it really comes down to expansion, how the piston's going to expand. The piston guys really have a tough job. They're looking at, okay, we're putting an educated, I hate to use the word guess, but we're putting an educated design in here that we think it needs to be this much smaller at the top, this much smaller at the bottom. We expect the piston to grow this much when it gets hot, and it'll stabilize itself in the bore, and it won't have a lot of rock. Well, that doesn't always happen because, again, they don't know every single detail about your engine. Is it gasoline? Is it alcohol? Is it aluminum block, iron block, air-cooled, water-cooled? All of these things affect it. How long you run is it? Is it running down the 1/4 mile, or are we running it at Bonneville? All of these things affect it. Everything affects the other thing. So if you see a piston that's got more than about 30 thousandths rock at bottom dead center, that's starting to get suspect. You start seeing a piston that's got 50, 60, 70 thousandths rock at bottom dead center, that's almost always an alarm. And you really need to stop and kind of question things. I've had quite a few customers over the years within the same brand and same part number of piston all of a sudden have an oil control problem and a ring problem. And they checked one piston. They bought them, a year and a half ago, the piston had 25,000 rock. Same part number, later batch, now they've got 50, 60,000 rock, and they run into what they perceived as a ring seal problem. It was really a rockover thing. So we're going back to what we talked about before, is you want to check all the details. Those things that get unchecked or left unlooked at, those are what get you going back into an engine. If you really look at all the little things, you almost always eliminate all these problems before you ever put the engine together. And again, it's just one of those. It's not saying that there's anything wrong with this, but it's, again, we're back to everything. It's always those things you check. You're going to check wrist pin clearance. You're going to check ring gaps. You're going to make sure the rings aren't bottom in the groove. These are all things that are typically beyond our control. And if we don't check them, that's when a problem can come into. So again, back to, it's really not as piston to wall so much as it is rock over. And it's just one of those things that you need to check.
Excellent. Yeah, you can never be too careful. You can never check too many times, right?
That, boy, isn't that the truth? I would just say I applaud those guys that say they can throw one together in an afternoon. I've never been that fortunate.
Right. All right. Well, thank you, Alex, for that question. Keith, since we were kind of talking about the cylinders there a little bit, Brandon Vaughn asked about cylinder finish procedures with diamond stones. And he's asking, do you need multiple grits of diamonds, or do you use a single or brushes? And do you prefer using oil or coolant?
Well, I'll start at the back end, the end of that question, and work forward. You can use an oil or a coolant. They both work well. They kind of have different end results. Again, you've got to remember that fluid is not only a coolant, it is a machining fluid. It's a metal working fluid. So as long as you're seeing good, nice, bright, shiny cylinders, the thing to remember is the cylinder should always look like I'll call it like a freshly cut piece of aluminum. It should always be bright, shiny, silvery, sparkly. It should never be flat, dull, dark. If it is, then it's burnished metal. You've taken that peak and you've rolled the peak over. You didn't get rid of it. You just rolled it over. And what's going to happen as the engine's running is that peak is eventually going to wear off, and it's going to get into the ring groove, the cylinder, and become a very abrasive product. So the color or the look of the board is real important. So as long as you're getting that color, that real bright, shiny look to the cylinder, either one works well. We've used both and had good results with both. Now, as far as diamonds go, yeah, you're going to want some multiple grits. You're going to want a roughing stone, something to kind of hog out. There's a lot of shops, including our own. We don't even own a boring bar anymore. We hone. If 30's got to come out of the hole, we hone it. So we go with a 70 grit diamond and let it eat. So yeah, it's always a good idea to have some multiple stones and a good plateauing tool. Some people are able to plateau using a very fine diamond. Some people use a set of brushes. I personally have had very, very good experiences using a dingle ball hone. Yeah, and I can hear you all laughing at me. Ball hone? Hey, ball hones absolutely work phenomenal. It's a great tool. The little fiber brushes also work well. The one that looks like a ball hone with no balls on the ends. They leave kind of a weird look. It's kind of all over the place, but it's just a look. It's just affecting the peak. For myself personally, I generally use the diamond to lay in what's called the RVK, the valley number I want to get. And then again, for me personally, and there's lots of ways to get there. It's like driving to my house. You can get to my house a lot of ways, but the end result, you got to my house. Same thing with honing. There can be a lot of ways to get to the end result. It's what works best for you. For me personally, it's a ball hone. I'll bring it out to size, make sure my RVK number is where I need it to be. Then I start coming in with a ball hone. I'll come in 5-6 strokes, check it, 5-6 strokes, check it. And I go back to that check it. When it comes to honing, the profilometer is, in my opinion, a must-have tool. If you're spending the money to buy a good hone and spend the money on diamonds, what good is all of that if you don't have a way to check the surface finish when you're done? Nobody out there, myself included, can give you a written out specific path. People ask me every day, they want to know how to get to the numbers. And I can help you, I can point you the right direction, but it doesn't mean you're going to get there. And especially with diamonds are very, very affected by pressure. You can really change a cylinder in literally 1 or 2 strokes with a diamond. It goes just like that. They cut so very quickly. So having that profilometer and having that ability to measure that cylinder is in my eyes imperative. It's like porting cylinder heads without having a flow bench. I port the prettiest cylinder head you've ever seen. I beg you to find a better looking head than I can port. Now, does my stuff work? Absolutely not. You want to knock 40, 50 horsepower out of your junk? You put my heads on. They look good, but they don't work. Why don't they work? I don't have a flow bench. So how can I prove my work? Same thing goes back to the profilometer. How do you know you got the work you wanted? The other side of that, and I've spent many, many days at many, many shops honing blocks, within the same block, you will generally find from the front to the back of the block, they're not the same hardness. This all comes down to how hard the cylinder is. I've worked on blocks and pro stock stuff. We're just getting all 8 cylinders the same. We picked up double-digit horsepower numbers. And in pro stock, that's they spend tens of thousands to find a couple. And we picked up double-digit, just getting all 8 holes the same within the same block. All 8 holes were honed the same process, same procedure. What they didn't realize is the back of the block was about 20 points harder than the front of the block. We generally measure blocks in Brunel. It's not unusual to see a block change 10, 15 points, 20 points front to back. So in the back of the block, it took more strokes to get it the same as the front of the block. Now in that engine, did that engine have a blow-by problem? Nope. Did it make great power? Yep, won an NHRA championship. Did it smoke? Nope. Did all those things well. But it was leaving something on the table. Once we got them all the same, big power increases, simply getting all 8 holes the same. So having that tool is very, very important. I do like using diamonds. Vitrified stones work very well. The biggest thing I see in honing today in the modern machines is having multiple stones in the heads. The more stones you can put in the head, the less pressure it takes to do the job effectively, the less load in the cylinder, the less likely, or it will say unlikely, you are to push the bore out of shape. So using an ultra, a super abrasive diamonds, there's also CBN, cubic boron nitride. CBN works extremely well. I really like that product. But multiple stones is really one of the keys to getting good bore geometry, because getting that true straight round bore is every bit as important as getting that bore finish correct. Again, a little bit lengthy. I hope that answered your question.
Yeah. Brandon, thank you for asking that. Scott Prager is on the call and he raised his hand. Scott, I'm going to unmute you. If you're ready to ask your question, please go right ahead.
Yes, can you hear me?
Go
Yeah,
ahead.
I sure can.
Okay, I'm just wondering your thoughts on hot honing in drag racing applications. Recommendations on that, pros or cons?
Yeah, pros and cons. Pros are, Scott, anything you can do to replicate the running environment, whether it be drag racing, circle track, I mean, anything, anywhere, everything and anything you can do to replicate that environment is going to help you get that truly, better bore geometry. If we can, put the block into the situation where it's actually, as it is actually going to be run, we're going to have better bore geometry. We're going to have a truer, straighter, rounder bore, and that's always a good thing. Cons to the hot honing situation is it's just that. It's another process. Some guys don't mind taking the time to do it. They don't mind having the equipment to do it. They don't mind having 200-degree hot honing oil thrown on them. They don't mind those things. They think the advantage is there for them, so they do it. So the con is just the working environment, what you have to do it. And if that's not a problem for you, I think it's fantastic. I've seen very, very nice gains with hot honing. I think it's a positive thing, but I have a lot of guys I've dealt with over the years that bought hot honing rigs. They did all the work. End of the day, they just ended up saying, hey, it's just too much of a hassle. Got away from it. So I'm not saying they're right or wrong. I like it. I think there's an advantage to it, but at the same time, I've got a fair amount of guys that have gotten away from it simply because of adding that one more process to the process.
Very good. Scott, hopefully that helped.
Yes, thank you.
All right, we got a question from Jimmy Stray. Jimmy's asking about the height, higher pressure for diamonds, and how that affects the heads with a higher number of stones pressure-wise.
Pressure, again, especially with diamonds, it affects all stones, but especially with diamonds. And again, we come back to that handy dandy tool, the profilometer. This is the truth teller. This thing, It doesn't lie. It's going to tell you what you have, whether you like it or not. But as far as pressure, generally speaking, the more pressure you can put on the stone, or you put on the stone, the higher the RVK value. And that RVK, that's your valley depth. That's the trench in the cylinder that gives the oil the ability to hang on. Sorry, we're gonna go back to making a drawing. So if we're looking at a cylinder finish, it's kind of sort of like an echocardiogram. And you're getting these different values. This area, this low area, is referred to as the through depth. This is the RVK. This is the valley. What this is the ability of the oil, I'll call it the storage tank. This is the ability for the oil to have something to grab a hold of. Just because you're throwing the oil at the bore, I mean, this could be 70-weight gear oil in a fuel car. Just because you're throwing that oil up on the cylinder doesn't mean the rings aren't scraping it back off into the sump. That's their job. We have to give that oil something to grab a hold of. We've got to give it something to bite onto so it can create that mixed or moderate boundary area in the cylinder. And before we cut loose on this thing for Jimmy, I'll kind of cut to Lake and let him expand on that. But if we don't give it that area, the oil's not going to grab onto the bore. And that's where pressure comes in. You can increase this value without changing the stone by simply increasing the pressure. Now, if you have a profilometer and you're trying to achieve, let's say, an RVK value of 70, and you've put all the pressure on it, you put all the load on it, and you can't get to that number, that's telling you right there we need to go to the next more aggressive stone. So if you're using let's just say arguably a 320, and I want to get a value number at 70, and I'm just not getting it there, and I've got this thing up at 60, 65% load, it's telling you you've got to go to the next more aggressive stone. So go to that stone, but back the pressure off. The more pressure, the more likely we are to push the cylinder out around. So if I can't get that value with a reasonable amount of load, go to the next more aggressive stone, back the pressure off, go in, check that number, and see what you see as far as those numbers. To get that VK number, we want to use the the less aggressive stone that we have to, but we also want to keep that pressure down. But and like I said, you may want to cut to Lake because he can kind of touch on how oil and this affects ring seal, piston to wall, all of that.
All right,
yeah, I unmuted myself there, and I'm going to attempt to share my screen with hopefully. Oh nope, you said I can't do that. That's fine. Whatever.
Yeah, sorry, I think that's turned off. Sorry.
It's okay, no big deal. So like Keith was saying with the valley, that is the oil storage tank. If you think about ring seal, really it's kind of my best analogy is like making soup. Soup isn't just the hone, it's not just the ring, it's not just the piston, it's not just the oil. All those have to come together in order to create the seal, because that's what we're after. We're after good ring seal. Keep the combustion pressures above the piston so it can move the piston to make power. So you're trying to reduce blow by. And to do that, you have to have all those things working together. You wouldn't just take a cylinder head and bolt it to the block without a gasket. The oil acts as the gasket between the ring and the ringland, between the ring and the cylinder wall. So the oil is the gasket. So to have the gasket there, because it is fluid and can move, that's where that valley comes in, like he said, be the oil storage tank to hold the oil. That way you have enough oil available to be that gasket to help everything seal up. We went through that in the NASCAR stuff, and I'm sure Keith remembers it really well when we got into the mirror honing and everything was super smooth. Well, blow-by went off the map because we didn't have enough valley to hold the oil. And of course, we were using really lightweight oils, and then it made it even easier for the ring to move it away. And we tried to compensate with higher viscosity, but it really didn't fix it. What we had to do, put more valley in it, and bang, everything sealed back up and power is back, and that's the way to go.
Excellent. Yep. Obviously, we don't have to tell anyone that oil is important. So
yeah, kind of.
Yeah. All right. We're going to jump to James Hoover, who's going to take us into the diesel world here. He asks, what's the proper way to break in a diesel engine on the dyno? He's specifically asking about an 8.3 Cummins or a 401 or 456 Ford.
Well, you're going to break them in pretty much the same way we talked about before. but you're going to put a lot more torque, load to it because it makes a lot more. Basically, you're going to beat the nuts off of it. I'm just joking. You want to put it on again, like anything else. Get a load on it. You want to get a mild load on it, get it run in, make sure everything's happy in the engine, nothing weird's going on. And once you're confident with that, put that mild load, let it run for a little while. We've got to make it work. We've got to put a load on the engine to effectively gas pressure load the rings to get them to work. So again, same thing. You want to get it on there. One of the things you really want to watch, and this is gas engine or diesel engine, it really doesn't matter. You want to make sure the fuel curve's right. This is really, really important on a fresh engine. And especially the guys that are, putting aftermarket EFI systems on, and especially street cars that don't get dynoed and get that map corrected. I can't tell you how many guys that we deal with on a weekly basis and end up having a ring problem. They've overfueled a fresh engine. We've not given it that, and even really a remote chance of it working that ring and cylinder wall together to get those, to get that final working combination, that final lapping process done. And they fuel washed it. They put so much fuel through it, they're starting to break the oil film down. The oil film doesn't have the ability to lubricate correctly. And again, well, I'll let Lake expand on that. And you end up burnishing the cylinder wall. And that's a really, really common problem, whether it's diesel, whether it's gasoline. It's simply because it's overfueled during that time. So real important to make sure, like I said, the fuel curve's right and to get a load on it as quickly as you can. You got to get a load on an engine. The run stand guys hate me. I know I've got a target on my back. Those things are great for firing it up, making sure the valves are good, timing's right. Shut it off. Do not let that thing sit there and percolate on a run stand for an hour. You're killing it. You're pouring so much fuel through the engine. You're breaking the oil down. It's just not able to do its job, and you end up burnishing a cylinder. Doesn't hurt the rings. 99% of the time, it does not hurt the rings. It burnishes the cylinder wall. You've got to take it back apart, rehome the bore, put it back together. So try to avoid any unloaded runtime on anything. And like I say, toss at the lake, just talk about what excessive fuel does to the oil.
Well, it obviously kills the oil. The viscosity of fuel is always a lot lower than the oil, and it doesn't contain any kind of anti-wear additives and stuff. My experience, I saw it yesterday, 10 years as a certified lubrication specialist as of yesterday. But, in that 10 years of studying lubrication and looking at used oil analysis, I can tell you that 9 times out of 10, so at least 90% of the really bad, failed engine used oil analysis reports, fuel is higher than it should be. Fuel dilution is a really, really big problem. And like I said, 9 times out of 10, when you see a bad oil analysis report, it's going to have high fuel dilution. And that was probably the first domino that fell that caused the problems.
Very good. All right. Well, James, thank you for the question on the diesel side. A little something different. Derek asks for your opinion on what is a good compression ratio to run for a street car that sees about 10% road course track time.
Wow, that's a really loaded question. From a ring point of view, they really don't care. I'll say you're going to want to run as much as you can effectively with the fuel that you're going to run. So it all comes down to to detonation. How much can you get away with the fuel that you're going to run in the engine? One of the gentlemen I can speak to here, Kevin Studaker. Kev runs a drag week car. He's got a really, really nice EFI system on this thing. He's got multiple maps in it to run on everything from Q16 to E85 to 91 octane. And it's all different fuel curves, fuel mapping in the engine to get away with the fuel he's running. And I don't remember the exact number, but I know that thing's well over 14 to 1, maybe 15 to 1. And he's driven this thing all over the country. And, for a big old Chevelle wagon that runs 9s on a foot brake, not too bad. But again, it all comes down to what kind of fuel you're going to run and what state of tune can it be in, and not get it into detonation, because that's the evil demon. That's the thing that's going to destroy that engine. If you've got so much compression, so much timing, a camshaft that is tight on the centers and builds a lot of cylinder pressure, and then you put 87 octane in it and things rattling its way home, trust me, it's not going to go very long.
Very good. All right, Derek says thank you. Can Keith, I had a couple questions for you. I was curious, if you want to talk a little bit about maybe some of the areas of growth that you've seen for Total Seal's rings. Are there certain ones that do better than others? Are there certain applications that you see being used more than others?
That's an excellent question. Where I see the growth in our industry is there's a lot of, we'll say, non-traditional forms of racing that are popping up, that are becoming bigger and bigger all the time. We've got NHRA drag racing, we've got NASCAR, we've got Formula One, Australian supercar classes that we worked with forever, but more and more grassroots movement stuff all the time. The grudge match racing, no prep racing, to pulling tractors and mud bog trucks, and just a lot of non-traditional areas that that are becoming more and more organized. But you're seeing a lot more of that these days. And in this environment that we're in now, where most organized racing is all shut down, you can't believe the amount of phone calls I get every day with guys that, hey, racetrack's open. I talked to one guy yesterday about his track in Indiana. They're running 10 cars a day, 7 days a week. First 10 guys, we're in. And they're building their own format to do what they want to do. So I'm seeing more and more grassroots stuff, as well as industrial, aviation type applications, restoration. Really, all kinds of things are exploding. A lot of new directions that were, that are, I don't want to say new, but kind of new to us, newer to us. We've been doing rings for air compressors, pump, natural gas compressors, all kinds. But especially during this, it's amazingly busy. And it's a lot of end user guys out there that are diving into projects. I just did literally a 32 Packard the other day. This guy's wanted to restore for years. I just did a 65 Mack B61 truck. The rings haven't been available for that for years, so I'm making them for the gentleman. He's getting it running. It's been sitting for decades. So a lot of really neat. And any of you that don't know what that truck looks like, Google that thing. That's a cool looking old truck. I don't know what I'd do with one, but I kind of want one. It's cool. From what I understand, 2 shifters in it. Yeah, real interesting thing to drive. But more and more applications like that all the time. And like I said, industrial, from the aviation world to aerospace stuff, all kinds of things. The ring world changed a lot. There's a lot less companies out there making piston rings these days than there were even a decade ago. And most of those companies want, and I'm not picking on anybody, so please don't think that I am, but they want to do OE level volumes. They want to build a lot of one thing. And I certainly understand that from a business model. Total Seal, though we can do that, we're really a big job shop. We love custom runs, small runs, prototype runs. We love the daily stuff too. That's our bread and butter, but I love doing custom stuff. And here, this is kind of perfect. I actually brought this in. I didn't expect to. We talked about that job shop thing. Total Seal is extremely known, or well known. We've been around since 1967. Company that developed the Gapless piston ring. So hopefully you guys can see this. Check this out. 1911 Benz. And I was corrected. I used the word Mercedes. They didn't merge till the late 20s. This is out of a Benz. This is a one-piece gapless piston ring. Check it out. Actually, if I can get it to come apart, like a spiral lock. I don't want to break this thing.
That's neat.
That's 1911. When I got this thing was 107 years old, and the gentleman came to us and wanted us to build these parts. And I went out to the shop, I talked to the foreman, and I said, now with all of our technology, all of our CNC equipment, all the things we can do, don't tell me we can't make this 107 years later when a little guy in Germany made this on a jack shaft driven lathe. It took us a little bit to figure it out, but we did it. And it just shows you, this is kind of some of the really fun stuff that I get to see and do. Besides the everyday racing applications. It's real fun. These pose some kind of cool challenges.
Yeah, absolutely. Well, Keith, I appreciate that. I'm glad to hear Total Seal's, alive, doing well, especially these last few months that the pandemic has thrown at all of us. I don't think we've got too many other questions here, so I'm going to wrap it up and again say thank you very much to Keith and to Lake and Total Seal. And to everyone who joined us on the call today, we appreciate you guys joining in. Before you guys all leave, make sure you do us a favor, follow Engine Builder Magazine, as well as Total Seal Piston Rings on Facebook, Twitter, YouTube. Instagram. You can find both of our brands there and get plenty more content and plenty more advice for your technical questions. So again, thank you very much to all you guys. Thanks for joining us. Keith, Lake, thank you very much.
Hey guys, I really appreciate this so much, and I appreciate you having on. And just one little last plug. I know we did a lot of questions, we answered a lot of stuff, but for those of you that didn't get an answer or didn't get to ask your question, hey, please feel free to reach out to us. Myself, Keith, Bobby Cheeseman, Kevin Studaker, Lake Speed. I think we've got one of the best technically involved, charged, whatever you want to call it, group of guys together here. It's really a great group of people. You know, between us, the amassed knowledge that we've got, I think you'd be hard pressed to find a better group of guys. So please, if you didn't get your question asked or answered, reach out to us. We'd love to tackle it.
Yeah, and for people who did ask questions and were a part of the meeting today, this video we have videoed this whole chat, so this will be up on the Engine Builder YouTube, hopefully in the next day or so. So you guys will be able to rewatch, go back through all the different advice Keith has given you guys today. So keep on the lookout for that. Again, thank you very much, guys. Enjoy the rest of your afternoons, and I hope everyone stays safe and healthy.